Hello all. As a continuation of my lecture series in control systems, now we are going to learn about stability analysis. So in the previous lectures, we have already discussed about mechanical translational systems, block diagrams and procedure for signal flow graph, continued by time response analysis. And after which stability is the main part, in which we have one methodology called Routh-Hurwitz Criterion in order to determine the stability of the system. So Routh-Hurwitz means we will form an array-like structure with the highest power of the given equation. So before going into this topic, why this topic is very important is, so when we come to the real world problem, so system instability leading to equipment damage. So stability is very important, which when it is unstable, then it leads to equipment damage. And who are all are affected when we see? Mainly control system are used in industries. So if this stability is not maintained, then control engineers and industrial processes gets affected. So what is the impact if it is unsolved? So which is equipment failure, significant economic losses and safety hazards to personnel. So these are all the main important things that we have to consider before going into this topic. Now, what we are going to do to find out the solution is, so complex polynomial roots. So when we go with solving higher order characteristic equations analytically, it is difficult and time consuming. So computational complexity, which is numerical methods, require significant computational resources for higher order systems. So indirect stability assessment like root solving provides stability information but lacks direct assessment method. So this is the need for the solution. Coming to the technological gaps, so direct stability assessment without root solving, predicting number of poles and analytical calculations, handling parameter variations in system design. So in this way, Routh-Hurwitz fill these gaps. So this is very beneficial to solve complex terms. Coming to introduction to Routh-Hurwitz criterion. So it was done by Edward John Routh, which is developed in the year of 1877, and Adolf Hurwitz, which is independent derivation, which was done in 1895. So the purpose, when we come into Routh-Hurwitz criterion, it determines the stability of linear time invariant systems without solving the characteristic equation. So characteristic equation and Routh array. So characteristic equation is 1 plus g of s into h of s is equal to 0. So general form is a power n s power n plus a power s power n minus 1 till a power 0, which is equal to 0. This will be the general form of the given equation. So Routh array will be a template which is shown in the right side part, which is by tabular arrangement of coefficients from characteristic equations. So we are just going to take the coefficients and form an array with the highest power and the next power. If the given equation is s power 4 plus 2 s power 3, then the first parameters we have to consider is even powers. So if the highest power is s power 4, then we have to consider s power 4 as the first parameter and corresponding even powers. Then the next thing that we have to consider is s power 3. That is the next order. So s power 4 and s power 3. With this consideration, we have to form an equation like this. So let us consider a characteristic equation like 1 s power 3 plus 5s square plus 6s plus 30. So for this characteristic equation, we have to form a Routh array, like first power was s power 3 and the next power was s power 2. So s power 3 coefficient is 1 and s power 2 coefficient is 5, and again s power 1, which is odd power, its coefficient is 6. That has to be brought it to the second row, second column. So the constant 30. So again we use formulas like cross multiplication, like 5 into 6 minus 30 into 1 divided by 5. Likewise, we have to solve till s power 0. Whatever may be the highest power, we have to solve till s power 0. And if the first column of the array is not considering any zeros or negative numbers, then we are coming to the conclusion that the system is stable. So here we have 3 steps So in the first step there is no sign change, second step and third step also we does not have any sign change. So therefore the system is stable. Coming to the stability conditions, so all coefficients of characteristic equation must be positive and non-zero. Sufficient condition is no sign changes in the first column of the Routh array. So if this condition satisfies, then we call it as the system is stable. We have another stability like it is moderately stable and it is unstable. So this condition comes to the end that when if it is there is no change in the first column and there is no zeros in the first column, then that characteristic equation we call it as stable. Coming to the applications in electrical engineering, so gain range determination, like find the range of gain k. So k value can also be determined. So if the characteristic equation contains an unknown variable k, we can find the range of k, not the exact value, but we can find the range of k that it varies from this to this. So this is done with the assumption of the system is stable. So feedback system analysis of closed loop control systems without solving the roots. Power system stability, assess stability of power grids and electrical networks under disturbances. So now let us summarize. So in this lecture, we have discussed about the Routh-Hurwitz criterion and its procedure, and when we are telling like the system is stable, and we have learnt about the computational of Routh array and stability conditions along with the special cases like first element consists of 0 and there is sign change, and we have discussed the applications. Thank you.